I just have a quick couple of slides. So hey everyone, welcome to DC207. If this is your first time, welcome and thank you for coming today. This of course is our May meeting. If you've never been with us before, DC207 is Maine's DEFCON chapter. We usually meet every third Thursday and we talk about InfoSec with a DEFCON twist. These are community-driven meetings, so usually no sales content or promoted things. So we like to keep it that way. Today we are giving away stuff, like always. Tonight we'll have a prize for a bus pirate, and you'll learn about in the presentation like why you want to have one of these. So you have to just stay on for the entire meeting, and then at the end we'll do a drawing and we'll give this thing away to a lucky person. Tonight we'll be featuring Nika Korchak. She's going to be talking to us all about hardware hacking. Her talk is entitled, "I'm sorry I rooted your smart home. I wish it was mine." It's very clever. So Nika actually came to me a few months back, and we talked a little bit about this idea that she had. And it's she's been, so Nika, you've been kind of like over this whole time period of this pandemic, you've been kind of learning how to do hardware hacking, and you just want to kind of share with people what you've learned and why this doesn't have to necessarily be confusing, right?
Yeah, exactly. Yeah, I've been working on some independent security projects, and I mean it's been a lot of fun, but it's a steep learning curve. So I was hoping to share some knowledge and help other people get started, and clear some of the hurdles that I ran into. So yeah.
That is so awesome. Well, what I'm going to go ahead and do is I'm going to stop sharing, and then I will let you start sharing, because that is all I have for slides.
Sounds good. All right. Okay. Okay. Just to check, can everyone see the presentation? Is it coming through?
Yep.
Cool. All right. So yeah, without further ado, let's get started. Hi, welcome. My name is Nika Korchak, and as Ben mentioned, I'll be giving my talk tonight on hardware hacking. So the talk is called "I'm Sorry I Rooted Your Smart House. I Wish It Was Mine," a modular anthology guide to go from zero to hardware hacking hero, or at least learn how to pop open a shell in your smart fridge. Okay, so part 0. Who am I? I'm a Tufts SMFA dual degree undergrad. I've been working as an independent security researcher, reverse engineer for the past year. And the work from this talk stems from all of that research that I've been working on, looking at security of embedded devices and IoT. I'm also an artist, and there's my socials. There's my Instagram, my Twitter, my website. Feel free to follow me and check out any of my art on my website if you're interested. Okay, so all right, so just a brief overview of the talk structure for tonight. So the talk is roughly divided into 3 parts. The first part is mainly theory, so it'll be definitions, sort of the background info that you need to get started working on the practical stuff. Practical is more in part 3 with the demo, but I'll be going back and forth during the talk to illustrate some of the points of the definitions. So I'll be using some of the examples from the demo to sort of further expound upon the definitions in the theory section. And then part 2 is the link between theory and practice. So it'll be how to set up your own hardware hacking lab, but on a budget. So, okay. So this is just a bit more detail about some of the stuff we'll be covering in part 1. Part 2, like I said, hardware hacking lab. And then part 3 is breaking some stuff. So, okay. So, why would you want to learn about hardware hacking and embedded device security? Well, as Anna Wintour famously did not say, but she's saying here in this meme that I made, patching your firmware is always in style. Or in other words, having the security of your organization compromised because no one patched the firmware on the smart fridge in the company break room, it's not a cute look. So we're going to be going over what firmware is, how to patch things, just some of the basics to help you get the fundamentals to understand different attack vectors and different important components of IoT and embedded device security. So motivations, IoT security is important. Good to know some basics. But also, what were my motivations for getting into hardware hacking and embedded device security? Initially, I was working on different research projects, but as I got more familiar, as I really leveled up my hardware hacking skills, I wanted to extend what I was working on to learn how to essentially create Mr. Robot-esque art installations using an IoT art botnet. Essentially just extending the hardware hacking tools, methodologies, skills that I'd learned and applying it to different creative pursuits. So there's lots of different interesting things that you can do with hardware hacking. It doesn't have to be necessarily, figuring out how to put in a rootkit or anything on your firmware. It's you can do lots of cool creative things. So maybe this talk will inspire some of you or all of you to get started with hardware hacking and create some cool projects. All right. So for this talk, I've created a reverse engineering methodology. It's a general overview of how I approach different hardware hacking projects and embedded device projects. This is what I've come up with during the last year with my research. So it's what works for me. It might not work for you, but it's just giving you a guideline of how to, go from zero to hero, or go from looking at a device and not knowing where to start to having something interesting at the end. So the methodology. So step one is recon and research. It's reading data sheets for the device, looking at the device, making note of any interesting features, anything that you would want to further look at as you're going down the line. And it also includes compiling relevant research that other people have done. So looking at talks from DEF CON or Black Hat or any CVEs that are out for the device that you're looking at. It's mostly just compiling lots of other research and recon. So step two, identification of access points on the device, as well as identification of interesting chips or anything interesting on the board itself. Step three is serial console setup and analysis. 4 is obtaining a firmware image. 5 is firmware analysis. 6 is identification of vulnerabilities on the device, but it could also be identification of interesting vectors to further develop for part 7, which could be exploit development or just art development, So that's our general overview, but because everyone likes graphs, here's our reverse engineering methodology, but make it Euclidean. So, and I'll be referring to this throughout the presentation, just as we go through these steps as part of the demo in part 3. So, and then just a quick note on the presentation format. Okay. So like I said, the talk is divided into 3 parts. And then in part 1, there's going to be quite a few slides that have this format. So the format of these slides is the right side panel is a scanned copy of my notes on a certain subtopic in hardware hacking. So this one, for example, is circuit schematic symbols. It's sort of a Rosetta Stone, if you will. And the structure for these slides is that they'll have on the right side, like I said, a scanned copy of the notes. The left side will have just a little descriptor of what they are. And these are really for your reference. I created this talk as an educational resource. So these slides will be made available afterwards, and you can refer to them. So I just wanted to include some more detailed notes on some of the more finer grained technical details that I won't have time to cover during the talk. So you can go back and use them and refer to them later. They can, I guess, function sort of as cheat sheets, if you will. So like I said, this one's schematic symbols, and then these are logic gates. So yeah, so I won't have time to go over all of the minutia in each of these, but you can look at them later and print them out, hang them up, or you know, you don't have to look at them, but they're there if you need them. Okay. Are there any questions now before we start with our definitions?
I'm
I have
actually.
a question. Oh, sorry.
No, go ahead.
Oh, I was wondering if there's anywhere I can find this slideshow afterwards. I'm a slow note taker, so sorry if that's a weird question.
Yeah, no worries. I'm going to be posting it on my website, and I think
Okay.
Ben, I'll probably send Ben a copy as well afterwards, and Ben can share it with the group on whatever forums.
Yeah, so if you signed up for the meetup, I can send out an email after tonight with a copy of the notes. We also will have a copy of the notes in the comment section of this video when it's uploaded to YouTube. So this will go up to YouTube, and you'll have that as a reference as well. So yeah, so I'll send all that stuff out if you're signed up. And if not, just drop me a PM with your email address and I'll send it out to you.
Thank you.
Yeah, and my question was just a curiosity: how many people here are EE or Comp Eng, Comp Sci background? So 0.
I have
I'm
a Comp Sci background. That's my background.
Is it Comp Sci or is that what you said? Mika?
Oh, yeah, my background, I got my one of my 3 undergrad degrees is computer science, so that's my background. But I didn't have, I actually didn't have any electrical engineering experience before I started working on this research project. So I guess just like a note where it says from zero to hero, that was me. I don't know if I'm hero, but I'm like some positive character. But when I started, I was, if I looked at a board, like a PCB, and tried to identify anything on it, I was lost. But now I can. So, but yeah, that's my background.
Okay.
Any other questions, or should I keep going?
I think you explained everything great.
All right, cool. All right, so, so we're going to go over some definitions. First of all, what's an embedded device? Well, an embedded device is a computer in miniature. It's a tiny little computer. You can put it in your purse or your pocket, or maybe you can't if you have a smart fridge, and it's probably not going to fit. But it's a small computer, so you have at least one PCB or printed circuit board, which will have a variety of chips that I'll go over in a few minutes. And there's a few different interesting challenges to working with embedded devices as opposed to maybe traditional desktops or laptops. But yeah. So for the demo, the embedded device that I chose to work with is this Foscam F19821W. The firmware version is that one. I got this from a yard sale, which is another good tip that I'll kind of be going over, touching on in part 2, just in terms of assembling materials for your hardware hacking lab, so that you don't spend a ton of money buying new embedded devices. Things like yard sales or Goodwill, secondhand shops. Those are a good place to get much more inexpensive devices just to play around with and get familiar with for your lab. Obviously, exercise caution if you're working with a device whose origins you're not familiar with. But yeah, like I said, it was cheap and I had it, and it was fun to play around with. So this is our device for our demo today. Okay, so one of the important parts for that step 1 research recon phase, when you're assembling your preliminary research, you're finding out information about the device that you've chosen. So here, the device I've chosen is this FOSS-CAM. One of the things you want to do is you want to just really look at the outside of the device, look at all of the different angles, and sometimes you can find really interesting and helpful information just from looking at the outside of the device. But this one was actually turning the device over. So this is a sticker on the bottom of the device. So you can't see it here, but if you flip it over, you get this. And this also has our very handy default admin credentials, which are admin and blank. As I was doing some of the research for this device, there's a lot of other talks that have been done, and a lot of other research that's been done on FOSS-CAM cameras specifically, and a lot of people have found this vulnerability, this default admin credentials. But a lot of people found it a lot later in the process. But here it is. It's right there, a sticker on the bottom. So it's just, I guess that's just a tip. Sometimes the most helpful information is right there in front of you. It just might be hidden or on a different side. So one of the first things that you want to do after you've looked at all the angles of your device, looked at the outside, also gone and gathered some additional research, is you want to start opening it up. You want to look at the inside so you can get to the PCB, the printed circuit board, which you can see right here. And in order to open up the device, you'll usually need screwdrivers, different tools just to open things up. An additional tip is when you want to figure out how to open up the device, because sometimes different manufacturers will have specific finicky things that they've done to make the device harder to get into. One thing that I do is I just do a quick Google or YouTube search, and I look for teardown of whatever device I'm looking at. So for this, I did a FOSS-CAM teardown search on YouTube, and I watched a couple other people take apart the device, which is just helpful so that these stickers are covering the screw head, so I have to take those off, which saves you just some time. Open up the device, and then here is, with all of those wires disconnected, this is just the PCB. So that's what an embedded device can look like on the inside. All right, so as I mentioned earlier, there's a couple of different unique features and challenges of working with embedded devices and IoT. So one of them is it's headless. So there's no, for the most part, there's not going to be an attached monitor for you to be able to see anything that's happening. So you won't be able to watch during the boot process any important messages that come up. And it's harder to interact with it. So in order to interact with it, because it's headless, you need to set up a serial console to see the terminal during important processes. And I'll go over how to set up a serial console later on in this part. And then the second unique feature or challenge is that it's almost certainly going to run an architecture that's not x86. So I learned ARM assembly, and I've been working primarily on ARM assembly throughout this research project. But there's lots of other assembly languages that embedded devices can run on. So there's MIPS and PowerPC. There's plenty of others. So the assembly language for the device is just going to depend on whatever the manufacturer used for the device. Okay, so any questions right now or no? Okay, we'll just keep going. All right, so okay, so we got our embedded device. We've looked at it. We've looked at the outside. Poked around it. We've looked at the PCB a little bit. But we want to learn more. So what's the best way to learn a lot about this device? It's the firmware. So what's firmware? Firmware is generally the intermediary piece of software that serves as the interface between the software and the hardware of a device. So in the case of embedded devices, the firmware image can contain a wide variety of interesting files. Sometimes it can be the entire OS kernel for the device. It can be like a compressed version of it. It can be a minified version of it. It can also, the firmware image of an embedded device can also contain things like READMEs, different text files that walk through things like the firmware update process, image files, what have you. So firmware can be, it can be a variety of things. But in general, it's going to be the piece of software that controls the device's functionality. So, and since it's so important for the device, it's going to be the main thing that you want to look at and use for determining different attack vectors or different ways to create cool art pieces. So, firmware traditionally can also be the BIOS, so it's the basic input-output system for a desktop computer, and it primarily resides in read-only memory or ROM. So it'll be on something like a flash chip or like a NAND serial NAND or serial NOR. It'll depend on the device and the data sheets that you find. But okay, so that's firmware. But how do we get firmware, right? So like this is nice in theory, but what does firmware look like actually? Well, there's 3 different ways that you can get firmware from an embedded device, or at least 3. I'll go over 3 general ones. The first one is obtaining it directly from the vendor website. The second one is you can get a firmware image by sniffing traffic during an important process, like the boot process, if you have a serial console set up, or something like a firmware update, watching and sniffing the traffic during that. And you can also get it by interfacing directly with one of the chips. So interfacing directly with where the firmware lives, which will be a flash chip. But let's start with the simplest thing, right? Let's see if we can find the firmware directly from the vendor website. So this is when I went to the FOSSCAMP website. I looked up all of the firmware versions, and lo and behold, it's there on the very bottom of the list. This is a very old version of the camera. It's from, well, old version of the camera, but it's from 2013, and it's got the oldest version of the firmware available on the site, but it's there. So we download it, and let's see what happens. Okay, so the first thing you want to do, or the first thing I did when I was doing some initial analysis on this firmware image, was run a couple of basic scans, basic utilities to find out some information. So there's file, which is the Linux utility, and it'll just it outputs the suspected file type based on magic byte signatures. So run file, get the information back, tells you it's an OpenSSL encrypted piece of data with a salted password. Okay, cool. But we probably want to confirm that with something else, right? Because it might not be 100% what that is. So we can run another one. For this, I use binwalk, which is another magic byte signature utility. It's open source. It's written in Python. It's on GitHub. It's great. So I ran binwalk with a verbose flag, and then binwalk also tells us that the file is encrypted with OpenSSL. Cool. And there's the salt. All right, so that's good. We have like pretty good confirmation that that's what we're dealing with. But this still doesn't tell us what the cipher is or the key. So, I mean, we could brute force it. We could run it with a bunch of word lists. We could see if we could decrypt it that way. Or we could just look at our other research that we found when we were doing our initial research recon. And, oh, look at that. There's a proof of concept piece of code on GitHub from one of the researchers who was doing research on this device. And it's got a firmware decryption script. Perfect. So this is what I used for decrypting the firmware image from the vendor website. On the, I don't know if you can see it, it's a bit small, but on the right side, there's a line that says command equals, and it's got the command, and then it just substitutes in the cipher and the key. The cipher that it lists is AES 128 CBC, and then here's an image of some of the common encryption keys. So, I mean, when you find things like this, you can either, download it directly or modify it, what have you. But I just used the information I found from this. I had the cipher, and then I tried it with the first encryption key that I saw, just to see if maybe because it was a really old firmware image, it would be one of the first ones on the list. And it was. So, cool. We have a decrypted firmware image, and we can poke around and look at some of the contents of it. So just to highlight a couple of the interesting files in the decrypted firmware image, we have an app directory. Technically, we have an app.tar file, but if we untar it, we have an app directory. We have a boot script. We have a firmware upgrade config XML file, and then a resolve config file. So if we look further in some of these, so here, if we just dig deeper into some of these files that we just pulled out of our decrypted firmware image, in the app directory, there's also a bunch of subdirectories. So if we look in the bin directory, there we go. So these are all the binaries that are included in this part of the firmware. So one of the interesting ones, there's a lot of really interesting ones here we could look at, but one of the interesting ones that I looked at was the firmware upgrade binary. And if we go back to here, there we go. When I was running, again, some initial analysis using the strings Linux utility, which will just tell you strings that are in a file, I was grepping for the OpenSSL string just to see if that was in the firmware upgrade binary itself. And it reveals that the exact command to decrypt the firmware image is in the firmware upgrade binary. So it's just a nice bit of confirmation that we had our right cipher and had the right key, and also that the key is hard-coded into the firmware upgrade binary. So, cool. And these are just some more interesting files. We have our boot. And then this is our last one that we're going to talk about, the firmware config XML file. If we just cat it, we're looking at some of the specs in here. We can see that there's 4 parts that are listed, or at least, let me say 4 or 5 parts that are listed here. But we only have one directory when we decrypt this, right? So we only had our app.tar. We don't see anything that's related to a Linux part, a U-boot, an NS-boot, a ROM part. Unclear if they're partitions or if they're just parts of the binary. I don't know how they're being distinguished in this file, but we know that there's probably more to the firmware image than what we got from the vendor website. So we probably want to dig further. Now, in order to dig further, we need to know how to work with the board, how to interface with the chips. So we're going to go over that now. Okay, so just to return to our reverse engineering methodology real quick, we're essentially at stage 2. So we did all our initial recon and research. We did already jump to part 4, and we got a firmware image from the vendor website. Did some initial firmware analysis, but it wasn't sufficient enough, or gave me reason to want to dig further. So now we're back at step 2, identifying areas of interest on the PCB. Okay. Any questions before I keep going with that?
I have one. During your reconnaissance, when you found that kind of decryption code for the firmware, let's say you didn't find that, then what would you do to kind of decrypt the firmware?
I mean, I'd probably just cycle through it with all of the listed ciphers for OpenSSL. I mean, I did write a bash script to do it, but it was just taking a long time.
Okay. Yeah.
But yeah, you can just cycle through all of the ciphers, which there's like 50 something, I believe. There might be more, and then run it with some word lists for common passwords. There's what's the one that I usually use? Daniel Meister is a really good one, like sec lists. It's on GitHub for security lists, for word lists, for brute forcing. But yeah.
Okay. Thank you.
Any other questions or no? Okay. Cool. All right. So integrated circuits. So yeah, as I already mentioned, firmware. Where does firmware live? Firmware lives on read-only memory, so it'll be on a ROM, on a flash chip, or some variety of flash chip, right? So we want to be looking at the board, trying to find our flash chip on the board that we want to essentially target for our further analysis. So there's two types of chips that I found to be the most interesting and the most replete with really quality info and places to just dig deeper and figure out more about the device itself. So those two types of chips are going to be the processor and the flash chip. So when you're looking at the board, you're going to want to be identifying candidate chips. So here I just have one circled on the right, and then this board has two sides where there's two sides of chips. And so on the opposite side of the PCB, we have two more candidates. And then in order to verify them, what you essentially want to do, or what I do, is probably take a magnifying glass, try and get really close to those chips, and then write down the serial numbers of all of them. And then using those serial numbers, go and search for data sheets that are the associated data sheets for those specific parts. And finding the data sheets can tell you what the chip is. And so here, this is our spoiler. The processor is this H1358. Yeah. And then basically repeat the same process for the flash chips. Identify flash chips, write down all the serial numbers, do some searches, try and find the data sheets. Once you find the data sheet that matches and that says it's serial flash or what have you, then you know that that's the chip that you want to be focusing on. So again, identify potential candidates. Same thing on the other side. We have 5 that could be the right one, and then again, spoiler, it's the one on the bottom right. So, and this is just the process of essentially Googling and digging through places like DigiKey, or even occasionally, if you have a really good verbose data sheet from the manufacturer themselves, you can find what the chips are that are used in that device specifically. But in this case, that wasn't true. So I had to look up each of these parts on their own and figure out what they were. So this is just one of our candidate chips that we can rule out as not being the flash. And this is our flash. So like I said, it's this on the bottom right. Also helpful to note that there's 2 little marks of, I believe, paint, probably added during development and testing by the manufacturer before it was shipped. That's just me guessing, but yeah, paint.
Yeah, that's a little odd. I thought maybe you did that, but that's a little odd if it came like that from the manufacturer.
Yeah. When I opened it up, those were on there, so I was like, it's probably that one, but I'm gonna double check. But yeah.
Yeah, I've seen that a couple times on chips. I think it's usually from, like you said, from QA. Like it's a QA marker. I'm looking at a board next to mine that has a similar marking on a flash chip. So.
Wait, what? Sorry.
Oh, I have a board.
I'll put my boom down so you can actually hear my voice this time. Yep, no, I've seen that same marking before on flash chips. I think it's usually from QA and manufacturing. The board I'm working on lately has the same marker on a flash chip too. So.
Yeah. So yeah, it can be helpful indicator that that's what you want to be looking for. And here's just some excerpts from our data sheet from the Macronix website. I don't know if I'm saying that company name right, but it'll be Macronix for right now. And yeah, the data sheet also gives you a lot of important information about what serial communication protocols the chip's going to speak. So there's lots of different potential serial communication protocols it can use. It can be SPI or JTAG or I2C or SWG. This one is SPI or SPI, and I'll be covering that protocol in this talk. And the other protocols I will leave you to explore further, but there's resources in the references for the talk to find other places to learn more about those other protocols. But this one speaks SPI, and which is good for us to know so that we know how to connect to that chip to get more information. So, all right, so just continuing on, figuring out how different chips on the board talk to one another and how we can interface with the different chips. So this is just a slide explaining a simplified view of communication between two computers. It doesn't look very simple, but it's essentially just a diagram showing that one computer will take a parallel input, convert it to a serial output. The second computer will take the serial input, convert it to a parallel output. That being said, the two serial communication protocols we're going to be covering here today are UART and SPI. So I'll go over this now. So this is a picture of the board with two candidate UART headers. So, and again, we're at part 2 stuff. So we're still identifying areas of interest on the board. We found our candidate chips that we want to look at, but we want to find where the points are on the board to connect for UART, which is going to be important for finding a serial console. I'll go over that now. Okay, so UART. What is UART? So UART stands for Universal Asynchronous Receiver and Transmitter. It's an asynchronous protocol, which means it doesn't use a clock to sync up the data transmission between two different communicating devices. So instead of using a clock, what it does is it has 4 important components. It has a frame size, a parity, a start and stop bit length, and a baud rate. So the baud rate is going to be the rate of transmission, so the bits per second. Frame size is frame size, parity, and start and stop bits. Generally, it'll be 8 and 1, but it can vary a lot. This is another instance where looking at the data sheets for the device and for the chips is going to tell you a lot of information about which of those specifications you want to list. So, but UART is what is going to be used when you're setting up a serial console. Oh, and the last important point to know, UART has technically 4 pins, but generally only 3 of them are going to be used when you're communicating with something using UART. So there's the RX, the TX, and the ground pin. There's also VCC if you want to provide power directly through that, but I generally stay away from that and just power the device using whatever power supply is built in. So when you're connecting to a UART or a UART set of headers, you want to connect the RX pin of the device with the TX pin of your USB to serial converter, and the TX pin of the device with the RX pin of the converter, and the ground to ground. So, and this is just another slide. It's just a brief note on TTL. So when you're using UART, it'll either be when you're connecting to something with UART, you're either going to be connecting to something with a serial to USB with a TTL or with an RS-232. Generally, the embedded devices I've worked on are all TTL, which stands for transistor logic. There's some devices that'll use RS-232, generally like older ones or like much bigger devices. But for the most part, you should be pretty pretty set with TTL, but again, it's something you just want to verify, just because like the sine waves for TTL and RS-232 are inverted, and RS-232 is like a way, it's a much larger range in terms of the volts that it accepts. So just something you want to verify. Okay, so that's what UART is, but what is UART useful for? UART's good for setting up a serial console. So a serial console uses a serial port connection to access a computer, allowing someone to interact with the device and send commands, and essentially watch a terminal emulator as the device is going through important processes like the boot process or firmware upgrade. So I use Minicom. I like Minicom a lot, but there's also a lot of other serial console programs you could use. There's QtCom and Putty and Screen and lots of other ones. But this is just setting up on Minicom. So, and as I mentioned before, you have your 4 important pieces of information to put in, which are the baud rate, and then you have your parity, your bits, your frame size. So on the right, you see line E. You have the specification for 115,200 for the baud rate, and then 8N1. And that's all you need to do to set it up. And then you plug it in and watch the serial console spit out all of the interesting information, ideally. Okay. And then the last communication protocol I'm going to cover is SPI. So serial protocol. Oh, yeah, sorry.
Yeah, I had a quick question. So, those settings that you just showed us there just a moment ago, how did you come to know that those are the ones that you need to use? Is that like common knowledge, or what was your methodology there?
For finding out you mean like for the 115,000 thing?
Yeah, like the baud rate and the settings that you need to set up that serial console.
Yeah. I think that was basically all just information that I learned as I was going through different tutorials, understanding how to interact with the UART, a device that communicates using UART, and then setting up a serial console. But yeah, that's just all the information that I found in all of my learning. Those are the ones that they always highlight.
Yeah, and as Nika had said, right, 8N1 is pretty common. The only thing you may have to really adjust is the baud rate.
Yeah.
Curtis did have a question down in chat that we missed earlier. He asked, is there a methodology that you follow for going through the chips that you were talking about earlier? Or, how do you go through that process of figuring out what they are without, falling down through a Google hole?
Right. Yeah, I'm just going to flip back to some of those pictures just to highlight it. So I guess in terms of identifying the chips, the main thing that I look for, I guess when you're looking at any IC, it's going to be some variety of black rectangle on the board, usually. I think in terms of the processor, you can usually identify it in terms of what it's surrounded by and like how many legs it looks like it has. So on the top right, there's one that's T and K, I believe, and I think that was, I have written down, I think it was either a voltage regulator or something else. Yeah, I generally look at the sizes and kind of just use, I guess, comparative analysis based on other talks and other research I've watched. Something else that's really helpful for figuring out what chips are what on a board is you can find the FCC ID number for the device itself, and then go to fccid.io or .gov and enter in the FCC ID number. And if the device has an FCC ID, generally there will be images that are on that site that are internal images. Not always, but there's like a good amount of devices have this. And so you can look at internal images of the device itself, and then sometimes those internal images will also include like annotations by other people, which indicate this is the processor, this is the flash chip, this is, you know, what have you. So that's helpful. And then I guess also one thing that can be a bit difficult when you're trying to identify components is, like I said, you probably want to use a magnifying glass or something, because the writing's really small. They're very small components. And sometimes the writing can also be like scratched off, or you know, if there's dust on it, or you know, if there's paint over it, like on the right hand side. Some of those other resources for I guess verifying that you have the right serial number for the component, that's helpful. So that was a bit of a long-winded explanation, but did that answer your question?
Yeah, you said FCC ID. That's a great idea.
Yeah, it's really helpful, and it includes a lot of other documents depending on the device. But yeah, lots of information you can get there.
That's cool. I'm gonna actually take a look at that, because I didn't know that the FCC ID had that kind of information. Very cool.
All right, so our last serial communication protocol we're going to be covering is SPI, or SPI. So SPI stands for Serial Peripheral Interface. So as opposed to UART, where UART is asynchronous, SPI is synchronous. So it uses a clock to sync up the sending and receiving data between the two devices. It'll use essentially 4 important pins. There's technically 8 pins on SPI, but the 4 that you'll generally need are CS for chip select, CLK, or some variety of clock, and then there's going to be either a MISO for master in slave out, or DO for data output, and then a MOSI for master out slave in data input. Those are, I guess, essentially equivalent to like the RX TX lines of the UART. And then in a SPI connection, you want to be hooking up the MISO to the MISO, the MOSI to the MOSI. So you have your device, you identify the chip and the layout of which pins are what on the flash chip, and using which pins are which, you'll connect it to your converter, your bus pirate, or what have you. But yeah, the important thing is that the MOSI goes to the MOSI, the MISO goes to the MISO. So all the chips go to their equivalent chips. So there's nothing like the UART where you're reversing something or inverting something, I suppose. And yeah. Okay. That's it. Anyone have any questions on SPI?
Yeah, what is the on the previous diagram? What is the SCK and SS? What does that represent on the?
Yeah, so the SCK is the clock, so that's just that's the clock speed that it's transferring at, and then the SS is the SS stands for, I guess, slave select, or it'll be chip select. I guess the important point of SPI is that it's one device controlling the other. So your adapter, your bus pirate, or whatever device you have that's going to be interfacing with SPI, that'll control the device that is on, or that'll control the chip that's on the board that uses SPI. So yeah.
Okay, thank you.
Yep. Okay. All right. So we have all our background knowledge that we need. So let's go into part 2 for setting up a hardware hacking lab. And like I mentioned before, this is the starving artist guide to setting up your hardware hacking lab. I think one of the big things that I ran into when I was getting started in this, and as I've continued to work on it, is it can be a bit overwhelming to look at all of the materials that you could buy, and know which ones that you need, and which ones you don't need, and also how to find essential parts of the hardware hacking lab that are not going to break the bank. So these are the ones that I have in my lab, and obviously other people will have different recommendations, but these are generally the essentials that I've found that you need. So first essential is jumper wires. So jumper wires will come in a variety of different configurations. There's MM, MF, and FF. Stand for M and F stand for male and female respectively. I don't know why, but they do. So, but I'm not a big fan of that naming convention, so I'm using M and F in this talk, but that's what they stand for. And then header pins. Header pins are good for connecting to small points on the board, especially for things like UARTs. I'll show that same photo in a minute. But a lot of UART headers on a board will just have holes, so you can insert a header pin into that and then connect another wire, another jumper wire, or a test clip to that header pin to start interfacing with it. So, jumper wires, header pins, and a serial to USB converter. This is actually a bus pirate. I like using my bus pirate for lots of different things because it speaks lots of different serial communication protocols, but really if you want to be interfacing with a UART, all you need is a really simple serial to USB converter, and you just want to make sure that it has both 3.3 and 5 volt settings, because those are the two most common voltage settings for small embedded devices. So the cost on each of these jumper wires you can get on Amazon and SparkFruit and SparkFun and Adafruit, packs of like 100 or so with a variety for $5 to $10, and then same with header pins in that same 5 to 10 range, just depending on how many you buy in a pack. And then a serial USB converter. I have an additional one. Actually, I can show you on my like camera here, but it's this. I don't know if y'all can see it. It's really small, but I got it on Amazon for I think $6, and it works really well. So you don't need anything too fancy for that. And the last essential is a multimeter, and a multimeter is going to be really, really important for testing continuity between points on a board and verifying what pins are what on anything like a UART, where you have 4 candidate pins, but you want to know which pin is which, so you know how to correctly set it up. So, multimeter. This one was, I believe, 30 that I got. I think that's generally the range for decent multimeters. You just want to make sure that it has a variety of settings for different things like direct voltage and for continuity and for resistance, for performing different tests on the board. All right, the next thing, it's not necessarily essential, but if you're working in hardware hacking, you're probably going to start soldering at some point. So these are all of the materials you need to get started in soldering. So first thing is obviously a soldering iron. You want it to be temperature controlled rather than just one listed temperature, or something that won't even display the temperature. You want to be able to control the temperature to adjust for different types of solder, mainly, because different types of solder will have different melting points. So you want to be able to adjust accordingly. Soldering iron and soldering iron stand, just so you can rest the soldering iron when you're working on different components on the board. This is flux. Flux is really important for making solder flow. Also really, really critical when you're working with lead-free solder, which doesn't flow as easily as leaded solder. You want to use some extra flux just to help the solder flow on the board. That's a silly philosophy joke for anyone who's also a Heraclitus fan. Otherwise, you can just brush past that. And then the 2 other things that you need are obviously solder, which comes in leaded or lead-free varieties, which is, take your pick, whatever you prefer to work with. For leaded solder, it has a lower melting point, as I mentioned, and lead-free solder will have a higher melting point. So just depending on what kind of solder you buy, you're just going to have to adjust your soldering iron temperature appropriately. And a soldering wick, which is a copper vacuum for sweeping up excess solder. It's just good for when you have too much solder on the board, you have to scoop it up. And then miscellaneous items for your soldering workbench. This is my makeshift soldering workbench. A kitchen sponge or a brass sponge for wiping off excess solder from the soldering iron between working on different components. A straight edge or a razor for scraping up excess flux that accumulates on the board. Isopropyl alcohol for cleaning up the board, good for like removing dust or any particles that accumulate on the board. A workbench, obviously, you want a flat surface to be working on. And then I also really like working on silicone baking sheets. It's just a starving artist hack because they're anti-static and good for resting materials. And then additionally, you might want to get something like a vice grip or helping hands to help hold small components in place while you're soldering and also holding the solder. Okay. And the last sort of category for soldering items is safety items, because safety is really important when you're working with very, very hot temperatures and things like leaded solder. So first and foremost, you want safety glasses to protect your eyes, obviously. A mask if you want to, protect from inhaling any solder fumes really directly. A small fan is good for blowing away some of those solder fumes, and also working by something like an open window or a suitable outdoor or semi-outdoor space, like a garage, or if you have access to an outdoor area that has good outlets, you can work outside. Now it's nicer out. And then the last two items, these are extra credit items, but I think they're really, really great. First one to highlight is a bus pirate. So as I just briefly mentioned earlier, the bus pirate is essentially a device that can communicate in a lot of different serial communication protocols. It doesn't do all of them, but it does a lot of the important ones. So it can speak JTAG and SPI and UART and I2C. So instead of having to buy a whole bunch of different small adapters, it's all in one. And I got this one from Adafruit for, I believe, 30, and then the just collection of, these are all jump bar wires with test probes at the end, so you can clip on to different small components on the board. I believe that was 8, so it was like 38 or 40, I think, approximately for this. And then also another extra credit item that you don't need, but it's helpful, Raspberry Pi. I got this actually primarily because Raspberry Pis are much more stable for working with programs like FlashROM, which I'll cover in a minute in the demo. But FlashROM is notoriously finicky on desktops, but works really well on Raspberry Pis. And it's also, Raspberry Pi is running on an ARM core, so it's a good environment to start playing with ARM binaries, if that's the assembly language that you want to be focusing on when you're doing your work. Okay, so those are all the materials. Are there any questions on any of that? Okay, so yeah, if there's no questions on that, I'll go through some more of the demo. Okay, so a lot of this we already covered earlier. Again, this is the FOSCAM. This is, let's see if we can go back to our, okay, so again, we've gone through a good number of these and then also gone back and forth a little bit. So we've done our initial recon and research on the device. We've found areas of interest. We've found interesting chips that we want to work on the board. And I'll be going over how to set up a serial console and then interface with one of the chips for further firmware analysis. So through this. So when you're confirming UART headers, so we went over the basics of UART. This is just when you find a candidate for a UART header, how do you proceed? So you're going to have 4 pins. Ideally, they would be labeled, so you would have labels on them indicating ground or VCC or what have you, but a lot of the times they won't be. So in order to verify them, you're going to go through essentially a 4-step process to verify each of the pins. And this is where using a multimeter is really handy. So you want to initially test and figure out which of the pins is ground, which you can do by performing a continuity test, which will just tell you, it'll essentially beep if there's little to no resistance between 2 points. And so when you're finding the ground, you want to be testing each of the header pins that you find to a ground point on the board, which can be something like any flat like other test point on the lower left. You have the 4 pins right there, and then there's like a little circle with a flat piece that can be a ground point. Yeah, when you find the pin that has the ground, you know that that's at least one of the ones you want to connect to. The other 3 you usually do confirmation of by powering on the device and then doing something like applying direct voltage to the ground pin and each of the 3 candidate pins, and just recording what the voltage levels are on those, and that can tell you what your RX pin is, your TX pin is, and which one your VCC is. And I also have some links in the references to some more detailed walkthroughs on how to go about that process a little more specifically. But yeah, once you have your UART headers confirmed, then you want to be connecting to your USB to serial converter, setting up your Minicom specifications or your serial console program specifications, so putting in your baud rate and everything, and then firing it up and seeing if anything comes through on your serial console. When I was doing this, I actually didn't get a serial console connection coming through, but there was also an Ethernet port on the device, and so I did a weird little I did a Wireshark packet capture using the Ethernet, and so I got information coming through on that PCAP that was indicating that packets were being sent. So I'm not sure what was happening with the headers on the board itself, but I did get confirmation that the information that I was suspecting would come through. Anyway, so yeah.
I had a question about that.
Yeah.
So at the voting machine hacking village at DEF CON, one of the people said, you know, this machine's not connected to the internet, and apparently there was an Ethernet port on the board. So I guess no one just looked at the board or something, but obviously you could just plug it in and like you said, use Wireshark. I was wondering, like, what about ones that aren't as obvious, like Bluetooth chips where or something? I mean, I guess you can look up the serial number, but do chips ever do more than one thing, like where there's hidden functionality, or is it always pretty much as obvious as like that chip does this because the serial number said this?
I think it definitely really depends. I think on a lot of, at least on the devices I've worked on for like embedded and IoT smaller devices, things like FOSCAMs, most of the parts generally will work as they're meant to, or as their data sheets indicate. But there is a really good resource as well. But I think it's also free. It's Andrew Bunny Huang's hacking Xbox, and he goes through some of this similar methodology. And on the Xbox, there's a lot of modified functionality that the Microsoft team put in, so that accessing like the flash chip wasn't easy to do really directly. So I think when you're working with with devices that have like a really big audience like that, then there's a chance that the chips or the headers or whatever aren't going to do exactly what you think they are. But for the most part, the devices I've worked on,
Yeah, and sometimes aren't they disabled after initial flash?
yeah, definitely.
Oh, that's cool. Thank you.
Okay. So once you confirm your UART headers and you set up your serial console, like I said, sometimes you can get something on the serial console that will give you a lot of good information. For my device, I didn't. I'm going to probably keep tinkering with it and see if I can get a serial console working, because I did watch a couple other talks and walkthroughs of people who have gotten it working. So it might just be my board. And this is another, I guess, just like a tip that I've come up with. So other people might find it helpful. One thing that's good for identifying components and traces on your board. So when you find a chip that you want to interface with, but maybe the pins are really, really small and you don't want to solder directly to the pins, or what have you. One thing that's helpful is to identify traces that connect the pins to different test points on the board. And one way to do this, other than finding data sheets or anything that'll tell you it directly, is to draw it. So I did some drawings of one of the other boards that I was looking at. And it's just helpful, I think, instead of tracing it directly on the board with your hand or something and getting dust or oil on the board itself. It can be helpful to try and make a drawing of it and just figure out what's connected to what and where different traces move on the board, so that you can identify, oh, here's the test point that I want to connect to this pin for the SPI. I find it helpful. Y'all can use it if you want, or if you don't like drawing, you don't have to. But I think it's a good way to create another resource for yourself, and it can also be good for just recording and having that information on hand, so you don't have to keep referring to a data sheet. You can make a drawing of the chip and remember which pins are which. So, okay, so post serial console, and then I guess post initial firmware, obtaining the initial firmware, or doing the initial firmware analysis. I guess we're at step 6. I won't flip through back to that flow chart again, but we're at step 6. So we want to interface directly with one of the chips using SPI to try and dump a full firmware image from the flash chip itself. In order to do this, you want to, sorry, that was a bug. You want to first confirm the pinout of the chip, as I said, know which pins are what, and then sometimes you can, or not sometimes, you can use things like test clips to clip directly onto the chip. I didn't have any of those, and the leads for the test probes on my Bus Pirate were a bit too large to clip onto the pins on this chip. So I just soldered wires directly to the little legs on the flash chip, and then once those are soldered, you can hook on to each of the wires, which are connected to your associated pins, and then hook it up to your Bus Pirate, and then run something like flash ROM, which will do different operations, but this one was just, this is the read operation to essentially read the full image from the chip. So this is flash ROM, and just indicating what the device is that you're using, and you're reading it, and that's your output file for the flash. And then once you have your full firmware image, or your full image of whatever's on your flash chip, you can just continue going forth with further analysis. I had a more working demo, but one of the very delicately soldered on wires on the flash chip broke. So, but from here, you would have your full flash binary, and you could isolate areas that you want to modify, and then reflash it onto the chip, or use something like the firmware upgrade binary that we found in the initial analysis and modify it that way. But yeah, that's our demo, and that's about it that I have. So, does anyone have any more questions?
So did you find any vulnerabilities in that device?
I did. I mean, well, the first big vulnerability was from, I guess, essentially step one, which is the default admin credentials, which are on a sticker on the device itself. And from a lot of the other security research here, I can flip to that slide. These are 6-7 write-ups of articles talking specifically about vulnerabilities in the FOSCAM cameras. Some of them are older. I think one of them was more recent. It was like 2018 or 2019. And the script that I used for decrypting was written by one of the security researchers at VDOO. So, but yeah, there's a lot of vulnerabilities with this device specifically that I didn't want to, it's a lot of ground to cover in terms of talking about all of the vulnerabilities. It's also a much older device, like a much older model of this device, and a much older firmware version. So it's kind of like shooting fish in a barrel to go after like a 2013 firmware image, but
Right.
but yeah. So yeah, lots of further reading. They're a very interesting device to look at in terms of security research. It's a very nefarious hidden functionality that was revealed by a lot of other security researchers. So.
I've got just a quick question about the drawings that you were making. Were those done with software or were those scans?
I drew them with like my pen and then I scanned it with my
Gotcha. Cool.
Yeah.
Nika, hi, this is James. This was a great presentation. Thank you.
Thanks.
You mentioned earlier that part of your incentive for hacking embedded hardware was for art projects.
Mm-hmm.
What have you used that for, and what have you created for your art projects using your knowledge?
Yeah, so I'm working on a new one right now. It's not done yet, but I was interested in figuring out how to have embedded devices essentially like creating their own artwork or exploiting the way different environments are understanding and translating different instructions. So I'm working on something right now that's essentially using monitors to model like one of the structures in a short story by Jorge Luis Borges. But yeah, that's like it's like connecting a bunch of smaller boards to show monitors for this visualization thing.
This sounds like another presentation.
Yeah, I mean, I'd be really happy to present on it once it's all done because I think it's going to be really cool.
That sounds fascinating. Yeah. Thank you.
Yeah.
We've got some nice comments in the chat. Folks really like the level of detail that you've been sharing. It's great feedback. And Envelope shared that one of her favorite soldering irons is really easy to use, gets up to temp fast. She shared that right in the link there. Is that like battery operated?
Is the soldering iron?
Yeah. Oh no, I'm asking Envelope if you're still there. Nope, she's got to go. Or thank you. Let's see you follow up with more depth. Yeah, cool.
So I think that's the, it's a USB-C soldering iron, if that's the one I'm thinking of, which is actually pretty sweet. You can use it with the power bank and stuff.
Oh, cool. Nice. The one that I have is like, it's got this big like base connector and then it has like a big cord. So anything small and nice is nice to have, like something you can pack away easy. I don't have anything like that right now, so. Cool. Any more questions for Nika?
Okay, so Nika, you know, do you have any smart devices in your house, and how are you securing them?
I don't have very many smart devices in my house, mostly because I'm very wary of them now. What are the? I think honestly, the majority of smart devices that I've been looking at and researching are just things that I found from like yard sales and things like that. I'm not big on like needing surveillance cameras and everything, but I usually collect things for the purposes of projects and like making art things.
I picked up a low-cost light bulb to play around with it, and it puts out some Bluetooth signals, it puts out some Wi-Fi signals, and you can only connect to it through an app, right? So there's some weird stuff, you know, going on there that I want to figure out. Not to mention the app, half of it's in another language. They don't even have the app translated properly.
Oh wow!
So it's one of those things. I've got it on a light switch, so I turn it on. I play around with it a little bit and turn it back off. Kill the power.
Yeah.
Sorry, go ahead.
Sounds like it could be like very, very interesting to look at it further, especially if. I think one of the things that's interesting about a lot of these devices is having functionality on them that you wouldn't normally think of as being necessary for the actual functioning of the device, like having a light bulb that's also synced to your Bluetooth, or that's also on your Wi-Fi, or like a lot of like, I think looking at like different like gaming processes that are running on these devices is also a very, very interesting place to explore. Yeah.
So Nika, has a lot of your research been around embedded devices that are kind of Linux based? Have you looked at other kind of more, I guess, more firmware based type of devices?
I would say like a decent amount's been Linux. I did spend a significant amount of time last year looking at like a hard drive, like a hard disk drive specifically. So that kind of had elements of both. But yeah, mostly Linux, a little bit more of some of the firmware. Yeah, like I said, I learned ARM. ARM's so cool too. Also, if anyone wants to learn ARM, I have a lot of good resources on the slides. I love ARM. That's all.
Awesome. Any more questions for Nika? Yes, Leon. More on that later. I set up like a smart device project like a long time ago at one of my jobs. So yeah. So anyways, cool. Well, Nika, thank you so much. This is great research. Thank you for sharing this with us. It's definitely a lot of information. I think you've really helped us understand this a little bit better and present it in a very digestible format. So thank you for that. Just give you a round of applause. Imagine everyone clapping. There's clapping. Awesome. So I'm gonna go ahead and I have a couple more slides. I'm gonna close out tonight's session. Just a couple things I just want to make folks aware of. All right, where is? Oh, Starlight is real. Share screen. All right. Okay, awesome. So next month, so we're on a break. So I just want to give you guys a heads up. On June, we're going to be resting, but we'll be back in July for more fun and games. On July 15th, we'll be doing a presentation called CVEs for Dummies, right? We're going to learn basic bug hunting in software and how to keep vendors honest through the coordinated disclosure process. So that should be fun. That's going to help folks understand, what is it really like to kind of go through the process of, finding bugs and reporting them, more or less. Next month, if you are jonesing for some sort of security content, I would encourage you to sign up for the OWASP main chapters event, which I'm actually going to be a part of. So OWASP MAME is back in 2021. You go over to owaspmame.org. You could actually sign up for the event, which is called Hacking Modern Web Applications. We're going to dig into the flagship product from OWASP called Juice Shop. And basically, it's a modern web application, an e-commerce application. And we're going to show you how to basically set up a whole Juice Shop for free online, use it for like a hacking lab, and do some experimentation with it. So it should be a fun event. I don't have a slide for this, but I did go ahead and spin the wheel. I put everybody's names in. So the winner of the Bus Pirate tonight is going to be Erica. Erica, are you still on the phone with us?
Yeah, cool.
Yeah. Is your address the same?
It is.
Okay, cool. I totally have her address for legitimate purposes. So yeah, anyways, but that's all I have for tonight. Thank you everyone for coming to DC207 and supporting it. I hope to see you soon. Maybe we'll see you at OWASP.
I'm joining from Texas, by the way.
Oh, awesome.
Yeah, several states away.
Hello from Texas. I'm glad you made it. A little bit warmer there.
Yes.
Thank you, Nika. Thank you, Ben. This is great.
Thank you.